Hello, my name is Aknur Karabay and I am a data scientist at the Institute of Smart Systems and Artificial Intelligence. In this tutorial, we will implement a program that simulates the spread of the COVID-19 epidemic. We will work on a particle-based SEIR simulator, where SEIR is the abbreviation of the four main epidemic states of a particle: susceptible, exposed, infected, and recovered. In this video, we will introduce a particle model and the epidemic state transitions. We will start with a brief explanation of a particle model with all parameters. The particle represents an individual that moves on a 2D map as shown on the right. Each particle has 5 parameters. The first one is x, which represents the position of a particle on a 2D map. The second parameter is v, the velocity of a particle. The next parameter holds the epidemic state of the particle. There are 6 states in total, and each of them is encoded by a numeric identifier. 0 is susceptible, 1 is exposed, 2 is infected, 7 is severely infected, 3 is recovered, and Z is 4. The fourth parameter is the duration of how long the particle spends in the current epidemic state. And the last one is the age group of the particle. On this graph, you can see that there are 9 age groups in total. Unfortunately, we know that in reality, certain age groups are at higher risk than others, and age differentiation helps us to incorporate different fatality rates for individuals and make a more realistic analysis. Here is the state chart of the simulator with the 6 states that we just introduced. First, let's cover the state transition parameters that we have. T, as mentioned earlier, is the time of a particle in the current epidemic state. T exposure is the time a particle spent in the exposed state. T infected is a diseased infection period during which a particle can be either infected or severely infected. Realistically, these two parameters would be 5 and 14 days. But for this tutorial, we will simplify it to 2 and 5 days. Beta is the rate of infected particles transitioning to the severely infected state based on the age group. And gamma is the mortality rate of the severely infected particles. Now, let's dive into state transitions of a particle. We assume that initially all particles are susceptible, meaning they are healthy. To start the epidemic spread, we will randomly select a subset of particles and assign them to be exposed. The particle stays in the exposed state for the disease exposure period and then transitions to the infected state. At this point, 2 things can happen. Before the particle's duration of stay in the infected state reaches the infection period, it may transition to severely infected state with the rate beta. Otherwise, it recovers. Suppose the particle becomes severely infected. When the particle reaches the infection period in the severely infected state, there are 2 scenarios. Particles may transition to the dead state based on the mortality rate, gamma, or recover. Note that in the beginning we simply initialize some of the healthy particles to be exposed, but in reality, they would have become exposed after being in contact with someone contagious. In our simulator, we consider exposed, infected, and severely infected particles to be contagious. After we initialize some of the particles to be exposed, at the beginning of the simulation, newly exposed cases appear based on the disease transmission condition. If the distance between a susceptible particle and a contagious particle is smaller than a certain threshold, then the disease is transmitted and the healthy particle becomes exposed. With this, we conclude the conceptual description of SEIR simulator, and in the next video,